If you line up the faces of 100 different people in your mind, what are their most distinguishing features? Which properties of a face allow you to recognize a person more than any other properties? And how can an algorithm accurately predict which movies you're going to like? We will tackle both of these questions with an extremely powerful tool from linear algebra, the singular value decomposition. The one discovery that drives everything in this video is that linear transformations turn circles into ellipses. This is obvious for a pure scaling where you stretch the horizontal and vertical axes independently. The corresponding matrix is diagonal, so the connection between diagonal matrices and ellipses is trivial. It's also obvious for a rotation, which turns a circle into the same circle, and that is a special kind of ellipse. It's less obvious for this shear transformation, which pushes the points above the x-axis to the right, and the ones below to the left. You can verify that even this transformation turns a circle into an ellipse. And here's a very extreme example. A projection onto a slanted line flattens the circle into a short line segment. You will have to think of that line segment as a one-dimensional ellipse. So the first question is, why? Why does this happen? Where do all those ellipses come from? Here's a really cool intuitive explanation that I found in a book about complex calculus of all things. The equation for a circle is quadratic. It's a polynomial that contains the squares of x and y. When we perform a linear transformation on it, there is nothing in this transformation that can change the degree of the polynomial. I mean, the x and y coordinates of every vector are just going to be multiplied with fixed constants and then added up. So the result must be another shape with a quadratic equation. Those shapes are known as conic sections. There are only three possible kinds of them: parabolas, hyperbolas, and ellipses. Now, parabolas and hyperbolas both shoot off to infinity. A linear transformation cannot do that. It can't turn finite points into infinite ones. And so the only other shape that is left on our list is an ellipse. This is such a clever and elegant argument. It should immediately give you the sense that our discovery is not a coincidence. It makes perfect sense. Every linear transformation must turn circles into ellipses. What we want to do next is decompose our matrix in such a way that its ellipse-producing behavior becomes explicit. What is the easiest way to draw an ellipse in linear algebra? I guess that would be with a diagonal matrix, right? Each element on the diagonal stretches one of the coordinates independently of the others. This stretches a circle into an ellipse, a sphere into an ellipsoid, and so on for higher dimensions. So we would love to have a diagonal matrix as the centerpiece of our decomposition. But there is a problem. A diagonal matrix can only stretch strictly horizontally and vertically, never at an angle. So if our ellipse happens to sit at an angle, we first have to rotate it into the horizontal vertical position. We must do this so that the x and y axes align perfectly with the main axes of the ellipse. This means that our decomposition must consist of three parts: a rotation that aligns the axes, followed by a pure stretching action, followed by another rotation so that our ellipse can end up at any angle we want. These are three extremely simple transformations that we already perfectly understand. The rotations that we do at the start and the end can also include reflections, so in general they will be orthogonal matrices. Orthonormal! And the one in the middle is diagonal. In a moment we will look at a concrete example from data science, and you will notice that the matrix in that example is rectangular. In fact, it will be extremely flat with only 2 columns, but potentially thousands of rows. The same decomposition works for such oddly shaped matrices too. It's pretty amazing that our decomposition can take any matrix, no matter how weird, no matter how rectangular, and pull it apart into a product of an orthogonal matrix, a diagonal one, and another orthogonal one. We will figure out how to find these factors later in the video. First, let's see what kinds of useful things we can do with our decomposition. I hope that by showing you two really exciting applications, I can justify why the singular value decomposition is seen as one of the most important in all of linear algebra. Ellipses turn out to be crucial in artificial intelligence and in data science. Let's look at that flat rectangular matrix first. It contains the heights and shoe sizes of hundreds of people. Each row is a person with two measurements, which you can think of as a 2D vector. But we will also sometimes treat each column as a very high-dimensional vector with hundreds of entries. Both of these views are useful. If we plot this data in a 2D plane, it might look something like this. We have lots of individual measurement points with their height on the horizontal axis and their shoe size on the vertical. Each dot on the screen is a person. You can see the vague outline of an ellipse in our data. It isn't perfect, of course, because this is real-world data instead of a clean mathematical model. So it contains a bit of noise, but you can still clearly see an ellipse. It slants upward, because on average, taller people have bigger shoes to fill. To analyze our data, we first have to move it to the origin. We just translate all the points so that the mean height becomes 0, and the mean shoe size also becomes 0. We now want to get an idea of the size of the ellipse. How wide and how tall is it? In other words, what is the spread of our data around the origin? In statistics, we use something called variance to measure how spread out our data points are. You may be aware that the variance is the square of the distance to the origin. The bigger this distance, the more your measurement deviates from the mean. And that's exactly what the variance intends to measure. We take the average variance across all people. So we run across all height measurements, we square them, and we add them all up. I hope that this formula makes your spidey senses tingle. This process of adding up squares looks a lot like the dot product between the vector of height measurements and itself. In other words, we end up with the square of the norm of this vector. And then we divide it by the number of data points to get the average. We can do the same for the shoe sizes. By rephrasing the variance as a norm, we can bring it from the world of statistics into the world of linear algebra. We can easily obtain these two squared norms by multiplying our data matrix with its own transpose on the left. The two rows of measurements get multiplied with the two columns containing the same measurements. That's how we get them squared. The matrix product then adds them all up, which is exactly what we want. At the end, we divide by n. The resulting matrix is called the covariance matrix. There are many interesting things to notice about it. First, even though our original matrix is very flat and rectangular, the covariance matrix is always square. In our example, it's a 2 by 2 matrix because we took 2 measurements for each person. If we also measure their weight, we get a 3 by 3, and so on. The second thing to notice is that the entries on the diagonal give us the variance of the height and shoe size measurements. That was intentional. It's why we constructed this matrix in the first place. I already mentioned before that the diagonal elements of a matrix tell you something about the self-interactions or self-connections, or in this case, the self-variance. You can see that the height has a bigger variance than the shoe size, which means that there is a bigger spread in people's heights than there is in their shoe sizes. This tells us in which direction the ellipse is more pronounced and spread out, and in which direction it's more flat. When you take the trace of this matrix, you add up all the diagonal elements to obtain the total variance across all measurements. So, just like in an earlier video, the trace can be interpreted as the total amount of self-interaction. And then there's that number off the diagonal. This is known as the cross-variance or cross-correlation, because it measures how much the height of a person correlates to his or her shoe size. If this number was 0, it would mean that there is absolutely no relation or connection between height and shoe size. But of course there is such a relation in real life. Bigger people typically have bigger feet. So the cross-correlation is positive here. You can see that the cross-correlation appears twice. The matrix is symmetric. We talked about why this happens in an earlier video. The product of a matrix with its own transpose is always symmetric. Another way to put this is that the cross-correlation is commutative. Okay, so we have already made some progress. We have a formula that measures the statistical spread of our data, or in other words, the size of our ellipse. And we can bring these ideas from statistics into linear algebra by constructing the covariance matrix. But the connection with the singular value decomposition isn't clear yet. Don't worry, it will become totally explicit in the final chapter of this video. We just have to take it one small step at a time, because there are lots of details we have to cover. These statistical ideas become way more useful in much higher dimensions. If you measure hundreds or even thousands of properties of people or objects or images, you end up with a huge covariance matrix and a very high-dimensional ellipsoid shape. What we have to do next is to order the variances from largest to smallest. Typically, when dealing with real-world data, one of the axes of this ellipsoid will be much bigger than all the other ones. That's the direction in which your data has the biggest spread, the highest variance. In our 2D example, that would be people's height. Then there will typically be a few smaller axes. Those are properties with a smaller but still significant variance. In our 2D example, that would be the shoe size. And these will be followed, typically, by a long tail of properties with a tiny variance. This gives us a good opportunity to separate the important properties from the irrelevant ones. If we throw those tiny properties away, we reduce the number of dimensions of our ellipsoid. This is a mega powerful technique in statistics and artificial intelligence. It allows you to compress your data so that it takes up less space. It makes your data more intuitive and easier to analyze. It basically summarizes your data without losing any of its significant detail. This technique is called principal component analysis, because we find the principal directions of the ellipsoid, the concepts with the highest variance, with the highest significance. We remove the others to get a clearer picture of our data. To make this very tangible, here's a cool and funny but absolutely real application. I honestly didn't make this up. We start with photos of thousands of faces. People's faces can look very different, so there's bound to be a huge variation. Each photo is an array of pixels, which we simply flatten into a single vector of grayscale values. That's how we get the input vectors for principal component analysis. Each vector is a face, and its properties are the grayscale values of its pixels. So, when we plot the faces in a very high-dimensional space, think of each axis as the grayscale value for a single pixel. We then calculate the covariance matrix for all these big grayscale vectors, and we find the directions in which the grayscale data varies the most. The results are incredible. Among the most distinguishing features of a human face are things like the distance between the eyes, the width of the nose, the roundness of the head, and so on. PCA discovers all of these features fully automatically, without even understanding what a human face is. Visually, you should think of the final ellipsoid as telling you that things like nose width and hairline are important concepts when talking about human faces. The algorithm discovers real-world concepts using only linear algebra. The axes of the ellipse are slanted with respect to the original basis, which means that each facial feature is a linear combination of many of the pixel values. That makes sense because pixel values don't really mean anything. PCA is basically begging us to rotate to a more meaningful basis. The algorithm finds meaning in large piles of meaningless data. It's quite remarkable that a simple blind mathematical technique can pull this off, without any knowledge of human faces at all. And so it shouldn't come as a surprise that this technique doesn't always work perfectly. Let's say that you run this experiment on a collection of photos that you just pull off the internet. Would you care to predict what the single most distinguishing feature in all these photos will turn out to be? Go on, try to guess. The answer, completely against all expectations, is the direction of the light. If you pick the photos from the web at random, roughly half of them will be lit from the left, and the other half will be lit from the right. And it turns out that this is the one feature that makes the biggest distinction between the photos. I think that's hilarious because it's just so unexpected. It shows that these algorithms are blind. They give you the correct answer, but it may not be an answer that you care about as a human being. The direction of the lighting doesn't matter at all when talking about human faces. So the lesson is that sometimes you have to throw away the first few principal components, because they just represent irrelevant aspects of your data. You could also make sure that you take all the photos under exactly identical lighting conditions to remove any irrelevant noise on your data. But the more important takeaway is that a simple linear algebra algorithm can uncover hidden concepts in huge matrices full of noisy data. That is quite impressive. Now that we have a good geometric understanding of the ellipse, let's look at the algebra. Here is a matrix of movie scores collected by an online streaming service or a movie database. Each row is a user, and each column is a movie. Will and Grace love science fiction movies, while Jack and Karen are fans of animation. You may also notice that there are certain movies that nobody really likes. If you have some programming skills, you could decompose this matrix using Python and NumPy. But it's much easier to just ask Wolfram Alpha, so that's what I did. It gave me these results. I will walk you through them, so that you can interpret what all these tables and numbers mean. We have decomposed our matrix into 3 parts: a rotation, an orthogonal stretch, and another rotation. It always helps to look carefully at how many rows and columns we have. The original matrix maps users directly to movies, so it's a 4 by 8 because there are 4 users and 8 movies. The diagonal matrix always has the same row and column count as the original, but it has non-zero numbers only on the diagonal. These are called the singular values. They're similar to the eigenvalues we had on the diagonal in the previous video. You can see that 2 of our singular values are large, and the other 2 are smaller. That's because the algorithm has discovered 2 movie genres. These are brand new concepts that were hiding inside of our data, like the facial features before. Again, it's quite amazing that a simple matrix decomposition can detect such concepts automatically. The first singular value represents the animation genre. The second one is the science fiction genre. The animation genre is a stronger concept, because our data contains 4 animation movies and only 3 sci-fi movies. Note that one of the movies has all 0 scores attached to it, so without any additional information, the algorithm cannot determine which of the 2 categories this movie belongs to. So that's why the animation category is slightly stronger. You can see that the SVD has ordered the singular values from largest to smallest. So even though the animation movies appear on the right in our original data matrix, they have been moved into pole position because of their higher strength. The 2 smallest singular values just capture the remaining noise in the input data, so they don't have any conceptual meaning. We would typically ignore them to compress or summarize the data. Now let's check out the first rotation matrix. It must be square, and you can easily see that its columns are orthogonal, because they never have any coordinates in common. The matrix is 4 by 4, and its purpose is to take us from users to movie genres. The first 2 users, Will and Grace, correlate very strongly with the second genre, but not at all with the first. That's because they love sci-fi but not animation. Jack and Karen don't care about sci-fi, but they love their daily cartoons. We will again ignore the other data because it relates to the 2 very weak singular values that we don't care about. So the first rotation maps the original concept of users to the newly uncovered concept of movie genres. Note that the users are still in the same order as in the original matrix. The SVD is free to reorder the new concepts it discovers, but not the concepts that we already modeled in the original data. Finally, the other rotation matrix is an 8 by 8, and it relates movies to movie genres. As expected, the final 4 movies correlate very strongly with the animation genre, and the first 4 with sci-fi. Well, not quite. The one movie that everyone hates isn't correlated to any genre at all, because the algorithm doesn't have any data for it. And again, we should ignore the rest of the data. We can throw it away because it's just noise and smaller details. So, if you don't mind me mixing a geometric metaphor with a conceptual one, what the SVD does is first rotate us from users to genres, then it tells us how relevant those genres are, and then it rotates us from genres to movies. The original data had a direct link between users and movies. In the SVD, this link now runs via the genres. The hidden intermediate data has been uncovered and made explicit. The ellipse is living right in the middle of this process. Okay, now that we've seen how amazing the SVD is in compressing your data and discovering new concepts, the final question is, how do we calculate it? How do we actually find the ellipse and the 3 matrices? First, a small remark about notation. Usually, the diagonal matrix in the middle is called sigma, because it contains the singular values. The rotation matrix on the left is called U, and the other one is called V, but we usually transpose it. The reason for the transpose is that we care more about the columns of V than its rows. It's a technical detail that you don't have to worry about too much. V is square, so the transpose doesn't even change its shape. Our goal now is to calculate these 3 matrices from the original matrix A. The trick that gets us going is to look at the transpose of A. The transpose of a product becomes the product of the transposes, but in the opposite order. And now we do something really clever. We multiply A with its own transpose on the right. Why is this so clever? Well, remember that V is an orthogonal matrix. From the video about matrix groups, you may remember that every orthogonal matrix satisfies this equation. If you need a quick reminder, This equation says that when you take pairwise dot products of a bunch of orthonormal columns, you get lots of zeros and ones, and they fill up an identity matrix. In our clever expression, we have managed to put V and its transpose right next to each other. They simplify to the identity matrix, so they completely vanish from the expression. We are left with only A and U, which is already a lot simpler. The next thing we do is write the product of sigma with its own transpose as a new matrix D. It's a square diagonal matrix, and it just has the squares of the singular values on its diagonal. Now for the final clever trick. Remember that the matrix U itself is also orthogonal, so it satisfies the same equation. But we can rewrite this slightly by multiplying both sides with the inverse of U. This shows that for any orthogonal matrix, its inverse is actually just its transpose. And so we can write this transpose over here as the inverse of U. This is our final result. This tells us everything we need to know. Do you recognize this kind of expression? If not, stare at it a little longer. We have a diagonal matrix in the middle, sandwiched between some matrix and its inverse. Did anyone say there and back again? This is a basis change. More than that, it's an eigenvalue decomposition. It calculates the eigenvalues of A transpose. Those eigenvalues end up in the diagonal matrix D, and the eigenvectors go into the columns of U. So we now know how to calculate the columns of U and the singular values. Just do an eigendecomposition of A transpose. By putting the transpose on the other side, we get a completely analogous equation for the columns of V. This is how you calculate all the parts of the SVD. The calculations hinge on a few important details. When you multiply a matrix with its own transpose, you always get a symmetric matrix. That's because we're taking pairwise dot products between the columns, and the dot product is commutative. But it gets better. Did you notice that this symmetric matrix is a covariance matrix? It gives us the covariances between the columns of A. You can also call this a correlation matrix, which gives me an excuse to remind you that the dot product measures correlations, remember? Now, there is a fairly simple algebraic proof that shows that a symmetric matrix always has real eigenvalues and orthogonal eigenvectors. You can find the proof in this video linked in the description. The point is that the eigenvectors of A transpose are orthogonal, so we can then normalize them to make them orthonormal. When we put them in the columns of our basis change matrix, the matrix automatically becomes an orthogonal one. That's why U and V are always orthogonal. This is one of the many ways in which symmetric matrices are incredibly nice to work with. I am leaving out many other details here. If you want to learn more, I've left many interesting links in the description. Don't forget to check those out, and to click the thumbs up to make our video reach more people. I mean, everybody out there needs to see those black and white faces, right? It would also make a huge difference if you'd support us financially on Patreon. Thank you so much. I want to end by showing you the most important differences between the two big matrix decompositions that we have discussed. The eigendecomposition from the previous video and the SVD. The eigenvalue decomposition only works for square matrices. You calculate the eigenvalues by taking a determinant, which is impossible for rectangular matrices. The SVD doesn't care about that. As we just saw, it creates a square matrix for itself behind the scenes. The product of a matrix with its own transpose is always square, so the input matrix can be as rectangular as you want it to be. Eigenvalues aren't always real. They are the solutions to a polynomial equation, which can have pairs of complex roots. The singular values, on the other hand, are always real, because they come from a symmetric matrix. And that's great because it means that we can always interpret these singular values as statistical variances. Eigenvectors are typically not orthogonal to each other. They can point in arbitrary directions. However, the matrices U and V in the singular value decomposition are always orthogonal. That's how we end up with an ellipse. The axes of an ellipse are orthogonal to each other. Finally, the eigendecomposition gives us a similarity relation between two matrices. The crusts of the sandwich take us to the eigenbasis and then back to our original basis. It goes there and back again. The SVD, on the other hand, uses two different matrices, U and V. The second rotation is not the inverse of the first. It rotates the ellipse into its final position, which has nothing to do with our original basis anymore. You could say that the SVD takes us there and then somewhere else.